Washington State University. Go Cougs!
Welcome back to our course on statistical inference. In Module 4, we will be looking at ways to evaluate the various models we've been learning. In Part 1, specifically, we'll look at different metrics to evaluate our models. Up to now, we've been using mostly accuracy to evaluate the models, but there are other metrics that can give us some more insight into the performance of our models. Before we define those metrics, first we need to cover some terminology, and that terminology is encompassed in what's called the confusion matrix. So the confusion matrix basically describes how we correctly or incorrectly classified various examples in our data set. The confusion matrix is usually described in terms of two classes called the positive class and the negative class. And so if a particular example, if its true class is positive, and we actually predict it as positive, then we call that a true positive. If its true class is positive, but we incorrectly predict it as negative, then that's a false negative. Likewise, if the true class of an example is negative, but we classify it as positive, then that's a false positive, should be negative. And if we do correctly classify it or predict it as negative, then that is a true negative. So the total number of positive examples in our data is P, the total number of true negatives is N, the total number of examples we predict as positive, right or wrong, is P prime, and the total number of predicted negative examples is N prime. And then M represents the total number of examples. So let's look at an example of the confusion matrix by running the naive Bayes classifier on our sensor data using all 9 of the features. And if we do that, these are the results we get. So of the 56 examples, 30 of them are their true class is play, and we'll let that be the positive class, and 26 of them are in the work or negative class. So of the examples that are truly classified as play, 28 of those we correctly classify as play, so those are our true positives. But on 2 of them we incorrectly classify them as work, and so those are our false negatives. For the examples that are classified as work, we get 25 of them correct, so those are our true negatives, but 1 of them we incorrectly classify, and so that is our false positive. So that's an example of the confusion matrix for our data on a particular classifier. But let's see how these different types of correct and incorrect predictions can derive some new metrics for us. So here's a list of the common metrics that we see to evaluate our learning models. Of course, accuracy we've already seen, and we can describe that in terms of our confusion matrix terminology as the sum of the true positives and true negatives divided by the total number of examples. Likewise, error, which is 1 minus the accuracy, we can define as the number of mistakes divided by the total number of examples. So the number of false positives and false negatives divided by the number of examples. Now, 2 other metrics that are commonly used for statistical inference are precision and recall. So precision is basically saying that of the positive predictions that we made, how many of them were correct. So we have our true positives in the numerator and the number of positive predictions in the denominator, whether they're true positives or false positives. Likewise, recall is saying that of the total number of positive examples, how many of them did we correctly predict, or the true positives. So we can represent that as the true positives over the total positives, or of course the same as true positives plus false negatives. Another term for this metric is the true positive rate, which we will see a little later as well. Now, to combine the precision and recall into one metric, we have the F measure, sometimes called the F1 measure, or in scikit-learn it's actually called the F1 score. And that is defined as 2 times the precision times the recall divided by the sum of precision and recall. And so all of these metrics, except for error, of course, we want them to be 1.0. That would be the best. Of course, error we would want to be 0. So these metrics give us a little bit more insight into the performance of our model, and specifically the types of mistakes it tends to make. Now, all of these metrics are available within scikit-learn in the metrics module. We've seen accuracy score. We've been using that quite a bit. We can also generate the 4 values inside the confusion matrix using the confusion matrix method. And we can also generate a classification report that includes the precision, the recall, and the F1 score in a table. It actually produces a string, and when we print that string to the screen, it'll give us a nice formatted report of those different metrics. So let's see that in action inside our Python code. So this is in the evaluation.python file. And so as usual, we're loading in our data. We're loading in the classifier. In this case, we'll use naive Bayes. And we're loading in the complete metrics module that we'll use several methods from. Next, we'll read in our data. Again, this is our typical way of reading in the data along with the classes work and play, and we're reading in all 9 of our sensor features. And as usual, we'll go ahead and fit our model, so we'll create a naive Bayes classifier and fit it to our data. And then we will use that classifier to predict the original data that we learned on and produce predictions in Z. Now, normally at this point, we would just come down to compute the accuracy score of those predictions and print it out, but we're also wanting to evaluate some of these other metrics. So we'll start by computing the confusion matrix. So this will compute the confusion matrix for the correct predictions versus our actual predictions. And the confusion matrix, of course, is a 2x2 matrix, and so we use this ravel method that essentially unravels the array of this matrix into one big long list. And that list will contain the 4 entries of our confusion matrix: the true negatives, false positives, false negatives, and true positives. So we'll print those out. And lastly, as I mentioned, the metrics module has this classification report method. Again, we pass in the correct and predicted classes. We also pass in the class names so that the report is a little easier to read. So if we were to run the evaluation Python, this is the output we would get. And I'll run it a little later because it does a few other things I want to explain. But one of the outputs is, of course, the elements of the confusion matrix, and then this classification report, and finally the accuracy of the model. Now, the classification report, you'll see, has multiple rows here: precision, recall, F1 score, and support, which is simply just the number of examples in each of these classes. And then it will produce an average of those metrics, and of course the sum of the total examples. Now, the reason there's 2 rows here is that, as you saw, the different precision and recall and F1 scores are defined in terms of positives and negatives. So this first row is treating the work class as the positive class, and the second row treats the play class as the positive class. And so actually it's the second row, play, is the numbers that we've been seeing in the previous example, because we were using play as the positive example. But you may want to use work as the positive example, or if you have more than 2 classes, then of course all of the classes get a turn at being the positive example, while the rest are treated as negative examples. So here are some additional metrics you can use to gain insight into the performance of your classifier. Now, one other set of metrics we can use has to do with how your classifier performs over a range of different classification methods for doing classification. So up to now, the classification has been kind of all or one. In other words, the classifier will say it's definitely work or it's definitely play. But if our classifier could produce a probability of work or play, then we could see more of a transition between guessing mostly play all the time, or requiring it to have a really high probability before it would guess play. So this is captured in what's called an ROC curve. ROC stands for Receiver Operating Characteristic, and this was a technique developed many years ago for trading off essentially the true positive and false positive rates that our classifier can generate. So first of all, in order to generate this curve, we're going to have to change how our classifier actually classifies things. As I mentioned, instead of giving a categorical answer that it's definitely work or definitely play, now we're wanting it to give us a probability distribution over the possible values. So if the probability of work is high and of play is low, then we'll tend to classify it as work, and that's what we've been doing. But if we do have the ability to produce a probability distribution over the classes, then we can do a little bit more interesting analysis in terms of trading off how strongly that probability, or how high that probability has to be in order for us to be confident that it's play or work. So what we can do then is, for each of the possible thresholds on the probability, we can plot a point on our curve. So for example, if we say the probability of play is, say, greater than 0.1, then we'll classify it as play, otherwise as work. So that will tend to classify most of them as play, because it's a fairly low threshold. If we increase this threshold to, say, 0.9, then the probability has to be greater than 0.9 for us to classify it as play, and so we won't classify as many of them as play. So if we classify a lot of them as play, then we're going to make a lot of false positives, because a lot of the work examples will be classified as play. If we make it very hard to classify something as play, then we'll get a lot of false negatives, because we will classify them instead as work, but in fact they shouldn't be. So as we vary this threshold theta, each time, for each value of theta, we get a point on this curve. And so what this curve is telling us is kind of the trade-off between, if we want to get more of the positives correct, in other words, a higher true positive rate, we're generally going to have to suffer a larger false positive rate. Now, these are defined as, the false positive rate is the number of false positives divided by the number of actual negatives, and the true positive rate, or recall, is the number of true positives divided by the actual number of positives. So again, for each choice of theta, we'll get a particular value for the false positive rate and true positive rate, and that'll give us a point on this curve. So the way we generate this curve is we vary theta, and as we increase theta, of course, we'll get a different result for the true positive and false positive rate and generate this curve. So obviously we'd like to live up here in the upper left, where our true positive rate is 1 and our false positive rate is 0. But of course most classifiers don't quite get there, as this one exhibits. So we also usually will plot this diagonal line, and this represents a classifier that's guessing at random. So we want to make sure that we're well above that line, otherwise we're not doing too well. So one way to compare these, obviously we can compare them visually and say, yes, we're well above the random line. But another way to do it is to compute the area under these curves and compare that. So I can compute the area under the curve, this upper curve, compute the area under the random curve, which will always be 0.5. And that's another way that I can generate a number to tell me how well my classifier is doing. So that's the area under the curve, or we usually abbreviate it as AUC. So that's an ROC curve, and then AUC gives us a number that tells us how well our classifier does kind of across the range of the types of mistakes that it can make. Now, scikit-learn also has the ability to generate the ROC curve and compute the AUC. But again, as we mentioned, to do that, instead of making a categorical prediction of the class, we want it to produce a probability distribution over the classes for each example. And so instead of using predict, if we use this predict probability method to do our predictions, it will instead produce this distribution as opposed to just work or play. Then passing in this probability distribution into this ROC curve method, that will produce a sequence of points to define our ROC curve. So the false positive rate, true positive rate points, and then we can plot that. And then in addition, we can pass those points into this ROC AUC score, and that will compute the area under the curve for that ROC curve. So let's see how to do that. So this is the last part of that same Python program evaluation. And so here we're computing the ROC and AUC. So here we're using the same naive Bayes classifier that we already trained or fit to the data. But now instead of doing predict, we're doing predict probability on our data, and that's going to give us a list or an array of probability distributions, each one of which is an array of probabilities over the different classes. Now for us, that's just work and play, and so each of those probability distributions is essentially two numbers, probability of work, probability of play. Now we're just going to generate the curve based on probability of play. So this line here grabs the second argument in a 0, 1 indexing. It's the index 1. So it will grab the second element of each of these probability distributions, which is the probability of play for each example. We pass that into our ROC curve along with the correct classifications, and that's going to produce our points, the false positive rate and true positive rate, the points on our curve. And it will also tell us the thresholds it uses and the values of theta, but we're not going to be using that. Finally, we can pass in the correct prediction or correct classifications along with this, the probabilities, and that will generate the area under the curve for this same ROC curve. And then these last few lines are simply generating this plot, giving it a title, plotting the points along the ROC curve, and producing a legend which tells us the AUC, placing that legend, plotting the random line in red, and limiting the X and Y axes to go from 0 to 1, and finally adding some nice axis labels for us. So that will generate the ROC and also tell us the AUC. So let's see that in action. So again, I'm in the code directory, and we're going to be looking at the evaluation.py file. So let's run that. So as we saw before, here is the confusion matrix information along with the classification report that gives us precision and recall, and finally the accuracy. And then we also have our ROC curve that's generated, as well as the AUC value of 0.97. So this gives us yet more metrics in which to evaluate our classifiers and some visual, which we can see how well our classifier is doing. Of course, we could run this on additional classifiers and look at their ROC curves as well as their AUCs, and gives us a way to compare the performance. Now, up to now, we have, let me go back to the notes. Up to now, we have been evaluating our models based on X, which is the data we use to fit the model. So it's very likely that our models would do very well because they're being tested on the same data that they've been trained on. In the extreme, the model could actually memorize the data and get perfect on it. But in reality, we'd like to know how well these models are going to do on examples maybe that they haven't seen. And so one way to do that is to set aside a separate set of data called a validation set. And then once we train our model on the training set, we then evaluate it on this separate validation set that it hasn't seen before. And that will tend to give us a better estimate of how it would work in the real world. One way to generate these validation sets is a technique called cross-validation. And in part 2, we will look at how to use cross-validation to give us a better estimate of how good our model is.